let's get started. So what is our goal? Again, so our goal is to find a local min or global, if possible, for the function f of x. Okay, or yeah, f of x. And here, f is a smooth real valued function and x is just some n-dimensional vector. That's our goal, again, is to solve this optimization problem. So min f of x such that x is a real valued vector. Okay. Now, because there are no constraints on the value of x, this problem falls under the umbrella of what's known as unconstrained optimization. Minimizing or maximizing a function subject to no constraints on the input vectors. Right? So, in general, like if we look at like two-dimensional space, something like this, right? We can have something like right here. This would be a local min, and then maybe something like right here. This would be a global min. So in practice, we won't be able to find global minimums, though we can sometimes. Typically, we'll be looking for local minimum, local extreme. And however, if the function is convex, this is convex right here, then there's one unique minimum, and we can find it. So, unique. Okay. So what does it mean to be convex? It basically means that if you pick any 2 points on the surface of the function, or the graph of the function, you can always draw a line between those 2 points which doesn't exit the function. For example, like if I pick this point here and this point here, right, and I draw a straight line between them, it remains inside the function. So that's a vague sense of what it means to be convex. If you pick 2 points on there, you draw a line, it remains inside the function. Right? So this would not be convex because if I pick this point right here and this point right here, and I draw a straight line between them, see that it exits out the function. It goes below the function's value. Whereas here, every point on this line is above the function. Okay. And I'll post another lecture describing the mathematical details behind convexity on YouTube. But for now, just know that it's always, the line between 2 points is always above the function. Okay, so how can we find this, right? So how can we find these extrema, these local and global minimums? Well, the easiest way to imagine it is if you're like standing on suppose you're like on a mountaintop, right? You're a mountain range, and it's pitch black, and you're trying to figure out how to get to the bottom, right? So if it's pitch black, you're going to use the gradient of what you're at the point you're standing on to decide if you lean forward, you're going to go downhill, or if you lean forward, you're going to go uphill, right? So the way that it works is by making use of the derivatives or the gradient. So for example, if I start with this point here, so this is like my x naught, right? And I'm evaluating where I'm standing on this mountain, and I lean this way. If I take steps this way, I see that I'm feeling that I'm going down, right? So I should go in the direction that this derivative is telling me to go. Notice the sign here is negative, so we want to go this way. So maybe we'll make another choice here. Okay. And then we'd evaluate the derivative again. And then we'd see that if we go this way, we'd be walking uphill. So we'd want to go in the opposite direction and go back this way. Maybe right there. Now, the amount for which we step is going to determine where we land, right? It's not only the sign of the derivative of the gradient, but it's how far we go, right? So the way that this is going to work is you're going to say that our new position is going to be our old position minus alpha times the derivative of the gradient at the old position. Because this tells us the sign and how much, right, how steep we're going to be increasing or decreasing. It tells us the direction of ascent, and this is in the opposite direction. Direction of ascent, opposite direction, and then here, this is called the learning rate. Or in optimization literature, it's called the step length. Now, strictly speaking, in terms of optimization from a mathematics point of view, you can choose a different step length or learning rate at each iteration. And there's actually quite a bit of work done on finding those optimal step lengths to ensure that you converge to your local minimum faster and you don't overshoot. But in practice for machine learners, for machine learning, this is fixed, so there's no k there, and you can use experimentation with your data to find the appropriate learning rate. If that thing is too big, like it was in our previous lecture, if that learning rate is too big, you can quickly find yourself having this kind of blow up or go nowhere, right? If it's too small, it won't converge fast enough. So it really is about experimenting with the size of that for our purposes here. Okay, so now notice over here, while we're talking about this with relation to convexity, since there's one unique minimum, so suppose we made a guess there, that was our first guess. So then we'd step a little bit this way, a little bit. We'd step a little bit this way. And we are going to run into this global minimum. And if we find any minimum in the convex case, it's a optimal. It is the global min, and we found the right one. Now, suppose if instead of choosing a small step length here, we chose a really big one, we'd end up over here. So our next point would be right across. So this is where choosing the appropriate step length is important. So let's go ahead and look at an example of how to visualize this in 2 dimensions using Julia. So let me share my screen here. Okay, so 1 second. Okay, so here I started a Jupyter notebook, which I've had a few questions about how your Jupyter notebook should look. Well, look at this markdown code here. I have a link to Unconstrained Optimization put in there. I have nice math equations describing what's going on. I have a nice little matrix here, and I have a description of what's going on. We're going to demonstrate this method, gradient descent, in this notebook. Okay, so now if I run that, I get this nice little picture here. And then also a heads up when you're doing this, see these 3 lines here? If I get rid of those, the cell kind of pops up just with the previous cell. But if I go down to the very bottom and I put 3 dashes in there, I get a line that separates my text from my code. It's just a stylistic thing that I find makes it easier to read Jupyter notebooks when you're trying to present them to people. Okay, so we're going to need a few packages today. So using plots, using random, using CSV. But note, CSV is deprecated, which means it's being replaced by using data. Okay, so this is the function I decided to look at. So let's go ahead and define this function. So f of xy is equal to 3 times x minus 4 all squared plus y squared. And then we can evaluate the gradient just by doing simple calculus here. So del, backslash del is how I get that symbol, f of xy. And the gradient is, of course, a vector. So it's the x component is the gradient, is the derivative of f with respect to x. So 2 times 3 is 6, and the derivative of the inside is 1. So it'll be 6 times x minus 4 is the first component. And the derivative with respect to y is just 2y. 2 times y. Okay. All right. So we have this loading here. So what I'm going to do is I'm going to convert this code cell to it should be CSV. So I made the next cell a markdown cell, and I'm going to do 3 lines there, 3 lines there. The following code cell plots 3-dimensional image of f of y. So we have that. So now we're going to plot it. So in order to do this, we need to give plots a range of values for x and y. So one way we can do that is say x is equal to, I played around with this with a little bit. So start at -5, take steps of size 0.5, and then end at 15. And then y will start at -10, and we'll take step sizes of 0.5, and we'll end at 10. So all this is doing is making quick partitions of values. So -5, -4.5, -4, all the way up to 15. That's all this is doing here. So then we can plot our function now by saying plot x, y, f, and then we're going to say that this is a surface. again, the first time you run plots, it's going to take a little while. So I'm going to go ahead and, so here's our picture. We see this looks like a pretty convex function, and that would be a convex function. And we see that there is a global minimum down here that we're going to try to find, right? Now, of course, we could set the gradient equal to 0 and solve, but we're going to do this iteratively. Okay, so it's going to be a little bit hard to visualize our points on this function. So what we can do is we can look at the contour plot instead, because it's easier to visualize in 3 dimensions what's going on. So maybe like for our learning purposes, we will visualize the contour plot of f of xy instead of the dimensional plot of the following code cell demonstrates how to plot this, something like that. Okay, so now we can just say, again, I played around with this for a little while, so I'm going to make my x range start at -100, go in increments of 0.5, and end at 100. And my y range to do the same thing, -100, go in increments of 0.5, and make it and stop at 100. Oh, didn't mean to do that. Now I'm going to say something like, I think I can do P1 is equal to contour of x, y, and f. And then we can say plot P1 legend equals false. So this is the contour plot of this function, right? Which is basically the projection here, where the minimum, the global minimum is in here, right? And the function is increasing as we go out, right? We see the values in color change. So 40,000 is the value over here, 35,000 roughly here, 5,000 roughly here, and then 0 down here where there's no, we've made it to the bottom. Okay, so let's go ahead and run gradient descent, right? So gradient descent is this method here. We make a guess, and then we subtract off, or we go in the opposite direction of ascent with step length alpha, or learning rate alpha. So I'm just going to do this by hand just for learning purposes, and say something like, I should put a cell in between here saying what I'm about to do, so this should be a markdown cell. But here I'm just going to go ahead and do it. So x naught, I'm going to say is equal to -1, 4. So that's my guess at x and y. And then I want to say scatter over the above plot. We can do this by saying f evaluated at x naught first entry of that vector, x naught second entry of that vector. Okay. And then I'm going to update my x and say x1 is equal to x naught minus, I'll pick a learning rate of 0.02 times del f at x naught. So x naught 1 is the x entry, x naught 2 is the y entry. And I can just copy that, paste. Actually, Let's not do that yet. Let me just see where we're at. Okay, so that's where our guess landed us, right? This is where we'd be on the function. So now if I just take this, paste it there. Now let's see where x1 is. Okay, so x1. Oh, see, we're moving downhill, right? We're going down this color gradient here. So let's just keep on doing this. Maybe I'll switch up the learning rate to be 0.2 or something, and this will be x2, x1, x1, x1. Now this will be x2, x2. And we're already at the bottom of the hill, right? In fact, we can verify this by saying, how can we do this? Let's just try to get this picture going here. So it's like, gotta make these triples here. X naught 1, X naught 2, and then F at X naught 1, X naught 2. Here's F like that. So now, just to make this easier, I'm going to just copy and paste 1, 1, 1, 1, and do this again, 2, 2. We probably won't be able to see it. I'm just like kind of curious to see if we can see the descent. Yeah, so you see we started at the orange dot, we went to the green dot, and then we're bottoming out over here near the global minimum. Okay. Okay, so next we're going to say, I would need a markdown here, so just a reminder that I need to fill this in later. I'm going to say subsection applications to linear regression. And then like insert, why is it doing that? I don't know why it's doing that. I don't know. All right, so here we're going to now read in this advertising data here. So data equals CSV dot read, and then give the name of the data. So dot CSV. So again, this deprecated message is because data frames is now how you can use CSV. All right, so that reads it into a Julia data frame. So what this data is it's sales, and then so amount of money, or amount of money spent on advertising for TV, radios, or newspaper versus the sales that they made for that that time frame. And so spent. So let's go ahead and maybe look at this data. And suppose, let's say I want to look at like spending on like radio ads versus the sales for that given time frame. So let's say we can, so I want to get, so x data is going to equal data dot, maybe TV, actually, let's look at TV sales. So amount spent on TV, and then the Y, or the labels will be data dot sales. And then I'll make some tuples of this. Data equals to x for x in zip, x data, comma y data. And do that. So we should have paired these up together. So let's look at a picture of this. Let's just scatter it. Scatter data tuples. And just the largest looks like 300 or something. So x lem equals 0 to 300. Y lem looks like they're all underneath 25, or I'll just say 30. 0, 30. Give it some nice labels. X-axis equals spending on TV ads. I'm pretty sure. And then Y-axis equals sales. Some scaled version of this currency. Okay. So that should be it. Oh, I don't want a legend. Okay, so our job is to find a line that fits this data the best we can. So notice that we have, so there's 200 tuples here, right? So there's 200 data entries, and we want to fit a line that best fits this. So just note that there's 200 data points. Okay, so okay, so we have x1, y1, dot, 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 x 200, y 200 as our points. Okay? So here we'll say that n, the number of data points, is equal to 200. Okay, and we want to find the best line again. So we want to find the best line, y equals wx plus b, that fits the data. Okay. So the way that we can do this is by defining a cost function or an error function. So what we're going to do is we're going to look at what's called the mean squared error cost function, otherwise called the MS. Okay, so we're going to use this. And what does it look like? So the mean squared error for, in this case, we have a slope and an intercept that we need to find. We don't know the slope and intercept ahead of time, but we need to find it. So the way that we're going to do that is by defining a function of W and V, which is the average squared error. So, and there's a few ways that you can define this function. It doesn't have to look this way. Sometimes you can have a 2 down there, sometimes it's just n. And this would be y minus yi minus wxi plus b all squared. So it's a mean squared error because that is averaging over all of them. What is it averaging? This is the squared error. It's how far apart our prediction is from the actual label, the difference or the error being squared. So that's where it gets its name, mean squared error. So now that we have this, right, we need to minimize this, right? If we can minimize the mean squared error, we're minimizing how off we are from our desired output, given a W and a B. So the way that we can do that is by using gradient descent. Now, what does that look like? Well, let's go ahead and say, this is probably too much. I'll just call it the cost function for now. But some people use MSV to represent this. So let's look at the partial derivative with respect to W. Okay, so hopefully all of you are familiar enough with calculus to see this, that we can sum across, so it's going to be 1 over n times the sum, I is equal 1 to n. So now we just look at it, and the derivative of each of these for I equals 1 through n. Well, what does that look like? Well, the derivative of the outside, right, is going to be 2 times this, right? So it's going to be 2 times y sub I minus wx sub I plus b. And then the derivative of the inside with respect to w, right, is just going to be negative xi. Okay. So that's going to be the case for every single one of these n terms. So there's always going to be a common factor of 2 and negative 1, right? So we can factor that out, and we get negative 2 over n times the sum from I is equal 1 to n of this stuff. Okay, so that's the partial derivative of this cost function, which we're wanting to minimize with respect to w. So this is del C, del w. Okay? And then if we look at the partial derivative of C with respect to V, right? Well, again, we have this 1 over n term times the sum from I is equal 1 to n of the derivative of this with respect to V. Well, the derivative of the outside is just going to be what is that? What did I put the equal sign there? 2 times the inside, right? So yi minus wxi plus v. And now the derivative of the inside, right, is 1. No, negative 1, right? Because that negative is going to multiply that b. So if you take the derivative of b, just the coefficient of b, which is a negative 1. There'll be a negative 1 out there, but we can just factor all that out and have a negative 1 right there. Okay? So these are the partial derivatives with respect to w and b, right? So now, let's go ahead and look at how we can do this now. So I'm just going to rewrite a few things. So we're trying to minimize this cost function. Okay. So just thinking back to what we were talking about with optimization, like what we want, right, is to find min WB of this, right? Before I had an X, but really like, you can think of X as like the two-dimensional vector with W and B in them, right? You see that? You can, it's just, I'm having two scalars is the same thing as thinking about having a function of a two-dimensional vector input. All right, so then what we want is we want like X k plus 1 to equal xk minus alpha times the gradient of f at xk, right? Where here, xk is just equal to some weight at k and some bias at k, okay? So another way of doing this in a simpler form, if you're not comfortable with working with these vectors, is you can just say that the weight at k plus 1 is equal to the weight at k minus alpha times the partial derivative. Oh, this is cost, sorry. We're minimizing this, right? So times the partial derivative of the cost with respect to W at the point WK BK. Together with saying that the intercept or the bias, the new one is your old one, minus alpha times your partial derivative of C with respect to B now at the point WK BK. Okay, we're starting at weight, we just subtract off an alpha times the partial, right? Now, this right here is equivalent to that update step up there. Okay, this is using vector notation, and this is just doing it component-wise. So what does this look like now? Well, WK plus 1 is going to be equal to WK minus alpha times that partial. Okay, so that partial derivative was given by -2 over n times the sum from I is equal to 1 to n of yi minus w times, this is the kth w, times xi plus bk, all like that, times xi. And then your bias, or your intercept, is going to be, so bk plus 1 is going to be equal to bk minus alpha times that thing up there, -1 over n times the sum, I is equal to 1 to n, yi minus your kth w times xi plus your kth b, like that. Okay, so one reason why I wanted to kind of work out these derivatives and show you this summation notation is that as we go further on, maybe not this week, maybe at the end of next week, we're going to start looking at neural nets in logistic regression, where we're going to encounter things that look messy, but it's really a simple idea of just taking a derivative and then going in the opposite direction at that with respect to that given variable. Right? Like in the w direction, we need to go this way, in the b direction, we need to go that way. It's the same thing as updating it with an entire vector. Okay. So now let's look at how to implement this. Okay. Okay. So let's go ahead and define our cost function. So C of a given W and D is equal to, let's say, 1 divided by the length of x data times the sum of, and now we just need to put in an array of the squared error. So I'll say y data I minus, and then I'm going to say w times x data I plus b. That's that, and then this is all going to be squared. And this is for I equals 1 to length of x data. And we already know what that length is. It should be 200. So let's go ahead and look at what this function looks like. So w equals, say, -50 with step sizes 0.5 to +50. So that's w ranging, and then b is going to be the same. And let's go ahead and plot this and see what it looks like. WB cost, and then this will be a surface. So notice that that this is a convex function, right? So this comes from all these square terms that we're looking at up here, right? And as I mentioned earlier, convex functions will have a global optimal that we can find. So if we apply gradient descent appropriately with appropriate step sizes to this mean squared error loss function or cost function, If we apply that, we're guaranteed to find eventually the global optimal that will find the best fit line. Okay, so let's write a function that just does an update on W and B, right? So call this like descent batch. Let me see, what should I call this? It's not going to matter. It's going to stay. No, I'll just do descent. So gradient descent. So batch gradient descent. That's what I'll call it. That's descriptive enough. I try to be as descriptive as I can with my functions. So this will take in my x data, my y data, w, b, and a learning rate alpha that we get to pick. Okay, so we're going to initialize, well, no, we have the formulas like behind me. I can kind of see them behind me now. We can just say W plus equals the sum of, so we're going to have -2, right? So -2 times x data I, that's like the x, right? Times, and then we have the loss, or the error, y data I minus w times x data I plus b. Close that off, right? For I equals 1 to the length. I'm gonna just, I don't want to have to type it over again. N is equal to the length of x data 1 to n. Okay, close that off, take the sum. Okay. I think that's going to work because we have the negative sign there. All right, and then similarly for B, actually, because this is so messy, the sum kind of makes it a little bit convoluted, but I'm just going to go with it for now. B is going to be, so now with B, what are we going to have here? We have all is the same except we don't have the multiplication by x anymore because the coefficient here was negative when we took the derivative. And then we just got to say return after that we have to make sure to divide by n, right? I guess I could just do that right here, like 1 divided by n, right there, times alpha times the sum. And just do that on both of them. And copy, so it looks very similar to what we did on the board. We are here. Oh, this needs to be W is equal to W minus that, right? And this needs to be B is equal to B minus that. So that should match up with exactly what I had on the board. Actually, if I were to make it look exactly like I had on the board, I would put the -2 out here and get rid of it in here. Just trying to make it look like the notes. Get rid of the -2 out there, put it right here. So this is the gradient with respect to W, or the partial with respect to W. This is the partial with respect to V. So then we can just say return WB. In that function out. Okay, so now this will take a single step. It will calculate the full gradient for every training example, and then we'll go down in that direction. So what we can say is like, okay, let's write a function that calculates our average loss. So function, so average loss for X data, Y data, W and B for a given W and B. Again, n is equal to the length that, and then total error, start off at 0, and for I equals 1 to n, total error plus equals, so let's just measure if we got it right or not, squared. So I minus X data I times W plus P, like that, square, and then we'll average out that, so return total. Actually, why am I even doing this? I have my cost function. The cost function should go down, so yeah, so I have my cost function. I don't need that. So, but we now can do batch training, and we'll take in X data, Y data, W, B, and learning parameter alpha. And also what's known as evbox. So this is just simply the number of times that we're going to calculate the gradient and update. So for I equals 1 to evbox, we just want to say W and B are going to be updated. So X data, Y data, W, B, and alpha. And then I want to go ahead and say, like, I want to print out what is going on here. So if I is equal to 1, I with cost, and here, this would just be cost, right? C, WB. I just want to print this out like every so often, just so I can see what's happening, to make sure that it actually is going down. And I'll do one more. And then maybe one more, just to see if we go anywhere different. All right, so then return W and B, end that function out. Whoa, oh no, had to end the for loop and then return W and B. Okay, so that should do it there. Just updating, calculating the gradient, updating W and B. Calculate gradient, update W and B. Okay, so let's go ahead and say, I already have a pre-made thing over here. So this is batch gradient descent. Batch gradient descent. X data, Y data. We're starting with W equal to 0, B equal to 0. Our step length is very small, and we're just going to take one step. What did I mess up? WB and alpha. Oh, batch train. That's what I meant to do. Batch train. Okay, so our initial cost here with one update was 58, and we see that we did make a line here. So now let's go ahead and do this, and let's do this like 100 times. Now we see that we got a better line, right? And if you try this again with like 1,000, so the second cost was 23. So let's go to 1,000. So you decrease the cost again. Now it's at 22 by just updating 22 times. Okay, or not 22, updating 1,000 times. Let's see if we can get it any smaller. Let's go 10,000 times. Okay. Now it did decrease, right? It's the cost. The lower the cost, the better fitting this line is to the data. Okay. Now, so what's interesting here is that notice that 10,000, right? It already took a second to run, right? And Julia's pretty fast. We're not doing it the most optimal way, but it's still, that's interesting to me. So the reason for that is that every single time we have to calculate the partial derivative with respect to W and B for every single one of these points, right? Now, if there was a billion points, right, calculating the full gradient is not going to necessarily be optimal, right? So what we can do is instead use something called stochastic gradient descent. So I'm just going to copy all this here and make some minor changes. So instead of batch means we're taking the full gradient. We're going to go stochastic gradient descent. And now I can get rid of this sum here. And what we're going to do, instead of summing over the whole gradient, we're just going to calculate for one data entry at a time. So I'm going to say I is equal to rand say like k n equals 1 to n. So what that is going to do is it's going to choose a random value from here, and there's 1 through 200. So it's going to pick a random I, and then it's only going to calculate the partial derivative at that one point. It's excluding all of the other values. It's only doing that. So now we can do stochastic train. All right, so this looks good. Everyone, hopefully you see that. We're only picking one data point to evaluate and change the derivative with. Okay, so just copy that. All right, so we made that. So now we just got to change this here. So this is 10,000. Let's see what it does. All right, so even though we were only calculating the gradient at one point instead of every single one of these, it's like calculating the cost at that point right here, and then only for that point updating W and B. It still looks like, so what do we have, like 21.83, 21.83, like it found the same W and B needed to get that kind of cost, right? Like if I run this again, see that little bit of slowdown there? And then here, it's roughly the same, but if the number of points has increased dramatically, stochastic gradient descent, as it's called, where we randomly select data points to update our WB from, will in general perform well. Okay. But we've run out of time. I encourage all of you to look up stochastic gradient descent as well as gradient descent. And then also batch stochastic gradient descent. Okay. And also you can play around with this data set by just like, instead of looking at TV sales, look at like newspaper sales or something. Is that what the column was? Newspaper, yeah. Like that. We have slightly different data. And just see what it does. Oh, you might have to adjust this. Right? And then you can still run this and you'll get like a different, that's like way off. We run it 100 times, starts to fit it, 1,000 times, 10,000 times. But then we can also run stochastic on it and see how that works out. And so I encourage you to play with this and find your own data sets. And then also from the beginning of the lecture, pay attention to how I was starting to put together the markdown tabs to kind of tell a story of what you're doing. Right? Okay, so that will be it for today. We will pick back up with another iterative learning algorithm next time. All right, and I'll upload this video to YouTube later today.